Okay then. So welcome back to the week 8 of the problem solving session for the course Fluid Mechanics and its Applications. So uh, we will wait for 2 more minutes. Let's see if others join, and then we would continue. If no other people join, then we will continue with the session. Okay, so I guess we can start now. Let's continue with the session, and if other people join, then we can uh, other people join, then it's fine. But right now, just to be with to be with the uh, s- schedule, I guess we need to start the session. Okay. So in today's session, we will be uh, elaborately discussing about flow through pipes. As an engineer, it's as an or I must say, in engineering perspective, flow through pipes is is one of the very important concepts from the subject of fluid mechanics, like pipes and piping networks finds its extensive use in the domain of engineering, and thus having a basic idea or basic knowledge of how the flow distribution takes place, or how the flow itself develops within pipes, is very important, and that's what we will be basically looking into in today's session. And as the name suggests, it's a very application type of concept or topic, where we will not be discussing, we will not go through the we will not dive deep to the very core of the derivation of the governing equations, because that we have already done in our previous sessions, and that's why we have built that's why this session, we have built up our concepts to understand this session, and this is the trend that will continue for the rest of the sessions, that we'll build up our concepts from our previous sessions and use those concepts for our for the following sessions, so that it feels connected, and you will see how we are able to connect our previous concepts, previously learned concepts, in today's session. So I must emphasize, I cannot emphasize enough the importance of today's session, at least in the perspective of an engineer. So I hope you focus today's session, and if you have any doubt, you can just stop me at any moment, and let's continue. Okay. So just for the in the starting, I won't go through dive deep to the flow measurement part, because I guess it's pretty self-explanatory, and like you can watch the lectures as well as watch the PPT given by Professor Gupta. It's very properly, he's explained different types of flow measuring devices and their applications. So I won't dive deep into that, but still, uh, uh, I would discuss one of them, that is basically pitot tube, that like I find that its application, I found it concept to be quite interesting, so I just wanted to discuss that. So you will see that most of these flow measuring devices are usually based upon the application of the continuity and the Bernoulli's equation. Okay, what they basically do is, as it is shown in this diagram, they create an obstruction in the flow, which results in a variation of the flow properties, specifically the velocity and pressure. and this variation in velocity and pressure is itself used as a measuring what to say measuring unit to define or describe other flow parameters such as mass flow rate. So mass flow rate basically like volume flow rate, then pressure difference, then these are what this is basically used. So we create an obstruction in the flow, which results in a variation of flow properties, and these are then used as a parameters to describe or define other flow properties, other useful flow properties that are used extensively in the engineering perspective, right? So that's what basically done. So you will see, here you will see the functioning of pitot tube. So there's usually very much a bit of confusion among the students on the application of pitot tubes and venturimeters and orifice meters. So I would emphasize that pitot tube is a flow measuring device which is used to measure the flow velocity. Okay, pitot tubes. This question usually comes in many competitive exams and in interviews itself. But what is the main application of pitot tube and how it is different from venturimeter or orifice meter? Like obviously, geometrically wise, if we see from a geometric point of view, they are obviously different. Their very construction is different. But if you go in the perspective of the applications, like sometimes people may get confused. So just to remove that confusion, I would emphasize that pitot tube is a device used solely to measure the velocity in the flow field. Okay. But venturimeter and orifice meter, like venturimeter and orifice meter, are used to measure the flow rate. Okay. See, I'm not saying that by the use of venturimeter you cannot determine the velocity, right? It can be done, but the sole purpose or the sole design or the sole objective for which this venturimeter and orifice meter were designed was to measure the flow rate. You will see in many in all the engineering fluid mechanics labs where there is a venturimeter fitted in the or I must say the venturimeter apparatus where it is there, you will see that the sole purpose of using doing an experiment is to measure the flow rate through that pipe or duct, right? So the sole purpose of venturimeter there or the orifice meter there is to measure the volume flow rate. But in the case of pitot tube, the sole purpose is to measure the velocity of the flow. So that's the main difference between the application of venturimeter or orifice meter and pitot tube. Okay. So again, the basic principles upon which the pitot tube works is very simple. Like we apply the Bernoulli's equation between 2 points in the flow field, and these 2 points are specifically selected in a way that one of the points lies in the flow field that moves along with the flow velocity, right? So at that point the velocity would be equal to the flow velocity in the flow domain. Okay, and the second point is used at the entrance of the pitot tube, which you can see here, where it is a very good approximation to assume that the flow velocity becomes 0. Okay, which is also very popularly known as the stagnation point, because the flow property because the flow velocity becomes 0, basically the flow becomes stagnant at that point, at that particular point. So it is known as a stagnation point. So if we apply the Bernoulli's equation between these 2 points, and assuming that this line is a streamline between point 1 and 2, you can see here that at point 1 velocity is equal to, like if we take velocity at point 1 equal to V and pressure at point 1 is equal to P1, then at point 2, as we said that the velocity at the entrance of the pitot tube is taken to be 0, so V2 would be equal to 0, and there is a pressure known as P2. So here you can see that since if these 2 points lie on the same elevation, then the potential energy part or the potential head becomes equal in both sides, so they cancel out. So we can see that P2 by rho g would be equal to V square by 2g plus P1 by rho g. Okay, And this pressure P2 is also popularly known as the stagnation pressure. Okay, so let me just write it. Stagnation pressure. Okay. So we'll just again modify the equation. We will just play with the numerators and denominators, and we can see here that V can be determined by square root of 2 del P by rho, because rho is again is an already known quantity, and this pressure difference can be measured by the help of a piezometer or manometer that is fitted in the flow field. So this pressure difference, if it is then if it's measured, then can be used to determine the velocity of the flow field. Okay, so that's the sole purpose of use of pitot tube. And again there's again I guess there's a brief discussion about pitot static tube. So as the name suggests, pitot as you saw that in the case of pitot tube, the pressure that we got at the entrance of the pitot tube was known as the stagnation pressure. So you can ideally say that pitot tube can also be used to measure stagnation pressure, right? So as the name suggests, pitot static tube, so you can clearly see that since pitot, if there's pitot if it is pitot static tube, it means that it's a combination of both pitot tube and there is some element of static pressure measurement. You can assume in that manner. So you can see that pitot static tube basically helps us in measuring both the stagnation pressure and the static pressure in the flow field. Okay, that is a design that is being made. So there's some static pressure holes in the pitot static tube on the outer periphery of the pitot tube. So at those points, if those pressure points are like used to measure the connectivity, connectivity with a piezometer, then those points will give the static pressure in the flow field. Okay, so that's why it is known as pitot static tube, as it helps us to measure both the stagnation pressure and the static pressure. Okay. So as I said, I won't dive deep in the in the flow measurement flow measuring devices part. Like, it's very self-explanatory. You can briefly go to the present PowerPoint presentation, or as well as you can attend the lecture by Professor Gupta. It's pretty self-explanatory, and like it's just an I would say, if you it's better if you do self-study upon that. Like, if you read it yourself, you will get better idea, and just to increase your your pool of knowledge, right? So it's very important to know various flow measuring devices and their working principles. So just for the sake of saving time and like saving time and covering the covering the concept that can be that is more conceptual. I have not dived deep in that part. I'm not saying that's not important. It's equally important, and as the name of the course itself suggests, it's an application based course, so it's very important you know the application. So I will emphasize that and request that to please go to the lectures by Professor Gupta on that flow measuring devices part. Also, if you want to save time, you can also just go to the PowerPoint presentation. It's very beautifully presented and arranged. So you can go to the presentation, then it will be very helpful for you. Okay then. So as I told you, today's session will be mainly dependent on focusing on this topic, that is flow through pipes. And as I already mentioned, I cannot emphasize more how much this topic or this concept is important in the as a perspective of an engineer. So okay, let's go to it. Okay, so we will just go to the basic definition that's written here. So while laminar flows are dominated by viscous forces, turbulent flows, I'm sorry, so that should be flows. Okay. Turbulent flows are dominated by inertial forces associated with large scale mixing. Okay. So In a geometrically similar flow, the transition from laminar to turbulent flow should occur at a fixed ratio of inertial and viscous forces. Okay, so as as it is mentioned here, that in laminar flows the pressure gradient it is the viscous forces that are being balanced by the it is the viscous force that balance the pressure gradient term, right? The pressure gradient that drives the flow is being balanced by the viscous forces. So in the case of, at least in the case of laminar flow, these are you can say primarily these are viscous forces viscous dominated flows, viscous forces dominated flows. So since as you know, as the name as you know that in the case of laminar flows, there are very less say it, or in the I will say in a different manner, like in viscous flows, like if at all there are any disturbances in the flow field, the viscosity of the fluid helps in mitigating the disturbances, or cancelling out those disturbances, so that these disturbances cannot lead cannot like amplify, which would have in turn led to the transition of flow to a turbulent flow field, right? Like if the flow is laminar, like it's predominantly laminar, then like if at all there are any disturbances, like I must say I can say in a way that like if at all there are disturbances, that might have amplified, like that might have disturbance in a such manner that that might have got amplified, and which in turn would have led to the transition of the flow from laminar to turbulent flow. Such kind of disturbances, or modes as they are specifically told, are being suppressed or diminished by the effect of the viscous forces or the viscosity of the fluid. So in the case of laminar flow, such disturbances are not amplified. So thus the flow remains laminar, right? Laminar in the sense that the flow moves very beautifully in particular layers, as the name itself suggests, laminar. So flow moves in layers, and there's a very what to say in a proper manner, there's a very good the flow moves in an arranged manner. There is no chaos at all. So there is a very good there is a high order, like the flow moves in a very orderly fashion, right? So everything is seems deterministic, everything seems like very simple. It seems like, and everything or in simpler terms, like it seems easy to be analyzed, like it seems that it could be easily solved analytically. So that's the, I must say, the very, what to say, basic nature of a laminar flow, which makes it like so likable, that it is so simple, so it can be analyzed very easily. The flow moves in a very orderly fashion, everything is in order, there's no chaos at all. So it seems like very friendly to us engineers and mathematicians. So that since the analysis is easy, so if the flow remains laminar, then it seems that everything is very easy. Like any analysis that can be done, that is possible to be done, can easily be done, because the flow is laminar, right? Everything is very simple. But just opposite to it, like in the case of turbulent flow, like everything that have defined for a laminar flow is just opposite in the case of turbulent flow. In the case of turbulent flow, the flow is highly chaotic. There is no order, like or you can say the flow is there is a very high randomness in the flow field. The flow is very highly disordered, right? And it almost seems impossible to analytically track the problem or analytically solve the problem. Like it seems almost impossible. So you may think why I'm discussing it so much. Like it is because most of the flows that we see in our day-to-day life are actually turbulent flow, right? And like the analysis itself, like I'm not saying at all that the analytical solution of turbulent flows are impossible. No, the analytical solution are like very, like in the perspective of mathematics, these are solvable problems, because we know these are defined by a Navier-Stokes equation. Like both laminar and turbulent flow can be modeled by the Navier-Stokes equation, so they are solvable. But the problem lies itself in the fact that the equations itself are so difficult to be solved that getting an analytical solution for even simple flows seems almost impossible. Then getting solution for turbulent flow, you can understand like how difficult it would actually be, right? So because of the very nature of the turbulent flow, there is high randomness, high disorder, difficult to be tracked analytically. So because of this nature of turbulent flow fields, people or researchers usually follow experimental methods or empirical methods to analyze turbulent flows, as you will eventually see in the later part of the session, that they used empirical relations to analyze the turbulent flow fields. They create different charts, models that can be used to analyze turbulent flow fields up to a certain limit. Like there's always a limit beyond which like their model fails. So different researchers create different models which work in different regimes of Reynolds number, and thus the limitation. There's no universal solution to the to the certain type of flow field, right? Even for same geometry, if the Reynolds number varies, then the solution breaks down, or the empirical model breaks down in the case of turbulent flow field. Okay, so I guess the explanation or the main difference between laminar and turbulent flow was clear. Like at least for right now, I just wanted to give the conceptual difference or the qualitative difference between Reynolds between laminar flows and turbulent flows. But as we go through the course, there will be various parameters or various quantitative there will be very quantitative methods by which you can differentiate between laminar and turbulent flows. Okay, so and one of those quantitative parameters that could help us to determine whether the flow is laminar or turbulent is known as Reynolds number. Okay, so Reynolds number, which is basically the ratio between the inertial forces and the viscous forces. So it is the ratio of inertial forces and viscous forces. So in the definition itself, as I mentioned, in the case of laminar flows, the flow is viscous dominated, right? The viscous force dominate in the case of laminar flows, and in the case of turbulent flows, inertia force dominate over the viscous forces. So as you can clearly see, it is not at all we are not at all trying to say that there are no inertial forces in the case of laminar flows or there are no viscous forces in the case of turbulent flows. No, both of these forces lie in the case in both the cases, in the case of turbulent flows and in the case of laminar flows. But it is the force or the driving force that dominates in the case of these two different types of flows, right? Because in the case of a laminar flow, the viscous forces dominate. In the case of, if you see in the Navier-Stokes equation, the pressure gradient term is being balanced by the viscous force terms, right? So it basically means that the advective term or the inertial force term is negligibly small or very small in the case of laminar flows. Okay, so that's why these forces are viscous dominated, and that's why, since these viscous force dominate, you can clearly say that if viscous force are higher or almost equivalent to the inertial force that exists in the flow field, you can say that the value of Reynolds number would actually be low, right? If the denominator is high, then you can clearly see that the Reynolds number would go down. Similarly, if you think in an opposite manner, in the case of turbulent flows, you can it clearly shows that the advection term, right, the advective term or the non-linear term in the case of in the left hand side of the Navier-Stokes equation, these terms actually dominate, right? These terms actually represent the forces that drive the flow, right? So that's why these forces are highly dominant in the case of a turbulent flow field. So that's why the inertial forces dominate over the viscous forces, and thus since the inertial forces would go up, it would directly imply that the Reynolds number of flow field will go up, right? So this is the very meaning of why the Reynolds number are higher in the case of a turbulent flow field and comparatively lower in the case of a laminar flow, right? But again, a simple definition of Reynolds number being high in the case of turbulent flow or Reynolds number being low in the case of laminar flows is not sufficient, right? We need a distinct demarcation that divides that below this value the flow would be laminar, or below or above this value the flow would be turbulent, right? So this demarcation, which divides the flow to be laminar or to be turbulent, is known as a critical Reynolds number, right? As it is mentioned here, the value of Reynolds number at which the transition from laminar to turbulent flow takes place is called the critical Reynolds number, represented by RECR, right? CR being in the subscript. So for a pipe flow, okay, it's very important. It's clearly defined that in case of a pipe flow, the critical Reynolds number is 2300, right? See, the value of critical Reynolds number varies, it's actually extensively varies depending upon the geometry of the flow. Okay, see, in the case of pipe flow it is 2300. In the case of flow through a duct, this value will change. Okay, similarly, if it is flow through a flow over a flat plate, the value of critical Reynolds number would change. If I am not wrong, I guess it's in the order of 5 into 10 to the power 5. Okay, so you can clearly see this difference, right? So in the case of a flow over flat plate, okay, I am not 100% sure, but because these are always remembered in the order of the Reynolds number. So as far as I remember, this should be the value of critical Reynolds number. Okay, and in the case of pipe flow, this value is 2300. Okay, so in some books, it's also maybe sometimes written as 2000. So that's not wrong. It depends on different authors, but 2300 is actually taken as a standard value. Many authors and many standard books have defined this value as the critical Reynolds number for the case of pipe flow. So it is usually we usually follow this value. Okay, but in some books maybe they may define it as 2000. So I won't say that's completely wrong, but again I won't say it's completely right, because most of the books that I have referred or authors that I have referred, I have seen this value to 2300. So you can, for right now, for this course at least, you can take the value of the critical Reynolds number in the case of pipe flow to 2300. Okay, again there is a term known as transition from laminar to turbulent. Okay, so I would say that this transition phenomenon from laminar to turbulent, I would say, is outside the scope of discussion for at least this session. Okay, at least for this session. So right now I won't dive deep into from transition to the transition of flow from laminar to turbulent. So I won't dive deep into that part, but I would just say that just for your understanding, below 2300 the flow is laminar. Right? It is what I must say, it is absolutely clear that below 2300 for a pipe flow the flow would be laminar. It's absolutely correct. But above 2300, if you say instead of 2300 I would say 2600. Now if I say that for 2600 a pipe flow is turbulent, that becomes a bit difficult to digest, I must say. It becomes a bit difficult to digest or accept that the flow was laminar up to 2300 and the flow suddenly become turbulent after 2300. 2301, the 2301 the flow becomes turbulent. No, that's not possible. It's not how physics works, right? It's not how nature works. It's not at all possible that there will be a sudden change in the flow properties for very minute change in the flow velocity, right? It's not at all possible. So that's why the concept of transition region comes into picture, right? There must be a region, or there must be a regime of Reynolds number between which the flow is neither fully laminar, neither fully turbulent. So flow is in a dual nature state. The flow has both the characteristics. There is some order in the flow, but certain regions of flow has some disorderness. So this this region, this transition region, is, like, I must say, is one of the very difficult uh, difficult concepts to master in the case of fluid mechanics. So it's very difficult because both nature of the flow field comes into picture, and it's very difficult to analyze, like, what governing equations would remain the same, but what relations would we use, what scales we would use to non-dimensionalize our equations and then solve them. So that becomes very difficult. So that's why it is very difficult to actually say that it's not correct to say that, I must say, it's not correct to say that after 2300 itself the flow becomes turbulent. So usually in the problems that you that we'll eventually solve, you'll eventually see that the value of the flow parameters, which basically the velocity or viscosity, would be given in such a way that if the flow is turbulent, you will find that the value of the Reynolds number would not be in this transition region. It will actually be around 4000, 5600, even 10,000. So if these are the values, 4000, 10,000, 5600, then you can clearly say that the flow is turbulent. Okay. So this is how the problems are being modeled or designed. Okay. So there's no issue there. But just to be very clear in this concept, that's why I'm emphasizing so much time in this concept. Like, usually students make a lot of mistakes in these concepts. So just to be clear, I'm emphasizing so much upon this concept. Okay. Again, thus, because just the qualitative definition of Reynolds number is not enough, and that's why if we deduce the terms that define the inertial force in the viscous force in the flow field, we will see that the Reynolds number can be defined as rho Vc Lc divided by mu, where rho is the density of the fluid, Vc is the characteristic velocity of the flow field. I guess we have discussed extensively about what is a characteristic velocity, what is a characteristic length scale in the previous session. So I will again discuss it when we discuss our boundary layer. But right now, just to keep in mind, Vc is a characteristic velocity. So we need to understand, like, obviously we've discussed this in the previous session when we're discussing about the Buckingham pi theorem or the dimension analysis. So there we saw what the characteristic velocity comes, what would be the characteristic velocity, right, when we non-dimensionalize the governing equations. Similar to that, so Vc is the characteristic velocity. Similarly, Lc is the characteristic length scale. So depending on a geometry, the characteristic length scale would vary. So it is very important for us to know, while defining Reynolds number, that what would be the characteristic length scale in the case of that particular geometry. So in the case of pipe flow, the characteristic length scale is actually equal to the diameter of the pipe. Okay, or some may take the radius of the pipe. Both are correct because they just vary by a factor of 0.5, right? Diameter is the radius is 0.5 times the diameter of the pipe. So the radius is 0.5 times the diameter of the pipe. So that doesn't make much of a difference. But still, if you ask me personally, like, what would I suggest? So at least in the case of pipe flow, for defining Reynolds number, I would say taking diameter as the characteristic length scale would be the ideal choice for determining the Reynolds number. Okay, so I will just write it because sometimes people may get confused. So for pipe flow, characteristic length scale is equal to diameter, and the characteristic velocity is actually the V average. Okay, the average velocity of the flow field, because I guess we have discussed it in the previous sessions, that how in the case of a pipe flow, the average velocity plays a very important role for which is usually taken as the characteristic velocity. Again, in the case of a flow or flat plate, it is the incoming undisturbed flow. This is basically u infinity. We take u infinity as the characteristic velocity. Okay, so depending on the geometry and the problem, the choice of the characteristic length scale and the characteristic velocity changes. Okay, so this actually comes by understanding, having a very high conceptual understanding, and obviously through practice. Okay. So again, I will just briefly go to the flow concept of entrance length and hydrodynamically developed flow. So as you can see, like when there is an incoming flow through a pipe, the boundary layers from both the upper part and lower part, like since obviously this is actually 3D diagram, so you can understand the boundary layer would develop in a three-dimensional way, like it will what to say, the boundary layer will develop throughout the circumference of the pipe, right? So there will be a, what to say, there will be a three-dimensional development of the pipe. Okay, I guess that is the correct term. So the boundary layer would develop throughout this circumference, right? Throughout the circumference of the pipe. But if we are just looking at a cross section, right? So in that manner, like if we see at a cross section, you will see that the boundary layers would develop because of the presence of the plate. The flow velocity will slow down in these regions because of the no slip condition. Thus, would result in the formation of a boundary layer, right? So the entrance length is determined by the length up to which these boundary layers from both the edges takes that length that up to which these boundary layers develop and merge to form a fully developed region or fully viscous region. It basically means that as we saw about as we briefly saw during the brief discussion on boundary layer, we saw that like this region is the viscous region, right? When we discuss about boundary layer, so this region tells that this is a viscous region. Within a boundary layer, the viscous effects dominate, and outside the boundary layer, so this is a potential flow region, right? So we can ideally say that in this region, the viscosity of flow is like, you can consider that the viscous effects of the flow to be quite low, mainly because of the fact that the velocity gradients would be quite low in those regions, right? So the viscous effects of flow are not manifested in those regions, right? In this potential flow region. So this region also known as the potential flow region. So after some time, these boundary layers would develop and merge at a point beyond which the flow is completely viscous, right? The viscous forces would be there throughout the flow, okay, throughout the cross section of the pipe, and that's why the point at which the these two boundary layers merge from the or I must say the distance from the entrance of the pipe to the point where these two boundary layers meet is known as the developing region or the entrance length. Okay, or if you want to say this length or dimensional wise, this length is known as the entrance length, and this region where the flow is developing, into a fully viscous region is known as the developing region. Okay, as you can, and here you can clearly see the velocity gradients would be there up till the boundary layer, and after the boundary there is a straight line. Okay, the straight line which manifests the fact that the flow is inviscid in this region. Similarly, I will just zoom it a bit. Similarly, in this region also the velocity profile is, if I do it correctly, the velocity profile should be completely straight. Okay, it should be completely straight. The viscous effects are only felt within the boundary layer. So outside the boundary layer, this is completely straight. Again, this will the velocity profile would take a curved shape because of the viscous effects, right? Similarly, the flow would develop. There would be a small straight region here. Then again, there is a curvature which is being manifested because of the velocity gradients. And also, like again, I guess it would be very great if we just to save time, I won't again dive deep to this concept again. But again, like one of the very important concepts is that in the case of pipe flows, the flow accelerates in the central part. Okay, you will see that the value of u at the center of the pipe, at least at this point, would be actually be higher than the incoming flow. Okay, if the incoming flow had a value of u, the value of u max would be higher than the value of the incoming flow. Okay, so the flow would accelerate in the case of a pipe flow, obviously by the virtue of mass conservation. Okay, so I guess that's all for the entrance region. So if you have any doubt, again you could please ask in the you can please ask, and if you have any doubt, you can, after the session also, you can just put those doubts in the discussion forum. Okay. So again, beyond this region, beyond the entrance lane, the flow is known as fully developed, and this is a very helpful concept or approximation that we usually use to simplify our analysis. Like you will see in the following derivation that this fully developed flow analysis actually helps us in helps us in simplifying our governing equation, or in turn also helps us in making our governing equations linear, which then helps us to get a which then help us to get a linear second order linear ordinary differential equation that is then very easily it is easy to solve, and thus there is an analytical solution for a pipe flow. Like after taking assumption that the flow is fully developed and steady, obviously after taking some certain assumptions only, we can say that we have a solution, we have an analytical solution for a pipe flow. Okay, so that derivation we will see in this in the following session. In the following part of this session. So okay, so again we'll see the entrance length of the pipe increases with the Reynolds number. Okay, so in the case of a laminar flow, the entrance length, basically this ratio of the entrance length by the diameter is given by 0.06 RED. Okay, RED emphasizes the fact that this Reynolds number has been determined with respect to the diameter of the pipe. Okay, taking diameter as a characteristic length scale. Similarly, in the case of turbulent flow, the ratio of the entrance length to the diameter is given by 4.4 into RED to the power 1 by 6. Okay. Sorry. And one more interesting fact to see to look upon is that the entrance length for a turbulent flow are much smaller than the in the case of a laminar flow. Okay, and this would ideally be because of the fact that the turbulent flow by its very nature is highly dissipative. Okay, and this dissipation is because of the fact that there is a very high level of mixing in the case of a turbulent flow field, and this mixing actually encourages or increases the level of momentum transfer between different fluid layers. Okay, which in turn results in a very very small entrance length compared to the comparatively very small entrance length compared to the laminar flow field. Okay, this high level of mixing in the flow field, which again increases the momentum transfer, results in a development of a comparatively smaller entrance length in the case of a turbulent flow field. Okay, this is again one of the very interesting characteristics of turbulent flow field. So I hope it was clear. Okay, then okay, there's a very long derivation on the flow through pipe, and this derivation is also important, so I cannot skip it, but still I will go a bit fast. I will just look in the equations, say how the terms are being cancelled out. So there might be some confusion in the derivation, they might occur, but if you have any doubt, you can please stop me at that moment itself, or then ask me how it is being derived, or you can just put that out in the discussion forum. Okay, so just okay. So we'll see the derivation for a flow through fully developed flow through a circular pipe or tube, which is also popularly known as the Hagen-Poiseuille flow. We discussed it in the case of the exact solution of a Navier-Stokes equation. So, but still, I will just revise it a bit quickly. So this is geometry like which we would solve using the cylindrical coordinate system r, theta, and z. So again we discuss the fully developed region. So this region is, we assume that our flow is fully developed, so the flow within the developing region is not being considered. So okay, so we take an inclined pipe, so where the again the gravitational acceleration are being decomposed into the sine and theta components, so which just helps in decomposing the body force terms. Okay, so again the governing equations would remain the same, that is the continuity equation and the momentum equation, which we'll eventually see. So and the main difference is that in the case of developing region, the velocity is a function of both r and z, but in the case of a fully developed flow, the velocity is only a function of r. Okay, the velocity component is only a function of r, and specifically you will see this u is actually uz, or the z velocity component. Okay, this is along this direction, which we'll eventually see. Okay, so the continuity equation in the cylindrical coordinate system is given by this equation, which will again we take one more assumption that the theta component, the derivative with respect to the theta component is 0 in the case of in this current derivation, and also will basically the flow is axisymmetric. So the derivative with respect to the theta is 0, that basically tells that the flow is axisymmetric. And also we'll take one more assumption is that the swirl component of the velocity, that's v theta will be taken to be 0. Okay, these are some assumptions that we take before deriving the equation. So v theta is 0. So given that fact, we will see that since the flow is steady, so this term will go out. Then since we told that the flow is axisymmetric, so dou by dou theta term is 0. So we're left with these two terms. Okay, again we take an assumption that since the flow is fully developed, dou vz by dou z is equal to 0, right? This derivation, this assumption. Okay, so we are left with only this term. So this tells us that r vr is not a function of r. Okay, again we see that at r equal to r, vr equal to 0. Okay, from the no penetration boundary condition, again vr equal to 0. This tells us that vr would be equal to 0 for all r except at r equal to 0, because this acts as a singularity point in the case of flow in this particular flow field. So except that point, since vr equal to 0 for at r equal to r, so it tells us that vr is not a function of r. Okay, and since vr is not a function of r, you can clearly tell, let's see if we can conclusively tell that vr is equal to 0 for all r or throughout the flow field. Okay, so this, since v theta is equal to 0, vr is also equal to 0, so we are only left with one velocity component, that is the vz component. So it essentially tells us that after applying some certain assumptions, we can simplify the flow through a pipe as a one-dimensional flow. Okay, so that is the sole purpose of taking this number of assumptions, so that the flow can be ideally taken as one dimension, which in turn simplifies the mathematics a lot, which in turn helps us in getting an analytical solution, which helps us to get an understanding of how the flow behaves in the case of a pipe flow. Okay, it may not be completely accurate because we are taking a lot of assumptions, but say that these assumptions are correct, then these are actually the exact solutions. Okay, if these assumptions are correct, then these are exact solutions. But again, the very application of these assumptions are not 100% like true or set or legible in the first place, right? But still, as I told you in the previous session itself, as engineers, it's not the exact solution, but the trend of the solution, or how the solution would behave, that matters, right? To get an understanding and then do the further analysis of the problem. Okay, so these solutions actually help us to get a trend of how the velocity profile would vary or would behave in the case of a pipe flow. Okay, so that's why these analyses are also very important. Then we look into the theta component of the momentum equation. So from that we can see that since v theta itself is equal to 0, and moreover the derivative with respect to theta is 0, we can clearly see that all the terms of the theta momentum equation becomes equal to 0. So we are not left with any conclusive remarks from the theta momentum equation. Then again from the r momentum equation, we can see that most of the term cancels out because the flow is steady. Again vr equal to 0, like from the boundary condition that we saw. Then again vr equal to 0, so right hand side is completely equal to 0. Okay, then dou p by dou r remains because we do not know how the pressure varies. Then vr equal to 0, then again we are left with the body force term. Okay, so the conclusive remark that we get from the R momentum equation is that dou P by dou R is equal to minus rho G cos theta. Okay, this is the first conclusive remark. Again, from the Z momentum equation, the flow in the flow steady, that this first term cancels out, Vi equal to 0, the second term cancels out, V theta again equal to 0, both these terms will equal to 0 because dou theta is also equal to 0 and V theta is also equal to 0. Then again, Vz is not equal to 0, but since we have taken a fully developed flow assumption, with this assumption itself ideally makes the right hand side of the equation completely 0, or also it removes the non-linearity of the equation, right? So this simplifies the governing equation a lot. Okay, the non-linear nature of the flow is completely removed from the governing equation. Okay, from right hand side again we do not know how the pressure varies, so dou P by dou Z term would remain. Then this first term will remain because Vz is a function of R in the case of fully developed flow. Again, dou by dou theta terms are 0, so this term goes out. Dou Vz by dou Z is equal to 0. This implies that the second order derivative would also be 0, so this is 0, and this term would remain. So the conclusive remark that we get from the Z momentum equation is that dou P by dou Z is equal to mu 1 by R dou by dou R dou Vz by dou R minus rho G sin theta is equal to, dou P by dou Z is equal to mu 1 by R dou by dou R dou Vz by dou R minus rho G sin theta. Okay, so from the R momentum equation we saw that dou P by dou R, dou P by dou R is equal to minus rho G cos theta. Okay, I just took all the terms on the same side, but like as I told, like if the radius of the pipe is not that large, okay, if the radius of the pipe is not that large, then this theta cos theta component is actually very small. Okay, it actually be very small. So obviously compared to the sin theta component. So we can ideally take this to be 0. It's also again very in a very good approximation, because most of the cases the length of the pipe is much larger than the radius of the pipe. Okay, so that's why this assumption is very good in that perspective. So we can ideally take dou P by dou R is equal to 0. Okay, so this in turn tells us that P is not a function of R. So that's why, since P is not a function of R and P is not a function of theta, because dou by dou theta terms are all R0 in the case of axisymmetric flow, so P is a function of only Z. Okay, P is a function of Z only. So that's why from Z momentum equation we can take we can convert the partial derivative of Z with respect to Z as a complete derivative. So now it becomes dP by dZ plus rho G sin theta is equal to mu 1 by R d by dr R dVz by dr. Okay, again you can see that how we have taken it as R, because we saw that Vz dou V by dou Z equal to 0. That's why we have Vz is function of R only. This we got from the fully developed flow assumption, right? So, and also from the continuity equation. So from that we got that Vz is a function of R only. So we can again change the partial derivative to a complete derivative in the case of the velocity in the case of the right hand side. Okay, right hand side also. So this dou by dou R can be converted into complete derivatives. Okay, so again this term on the right hand side can be again handled by taking the pressure in terms of a piezometric pressure. Okay, so we take P, instead of dealing with P only, we deal with P star now. So P star will be equal to P plus rho Gz sin theta. Okay, so obviously if we take the derivative of this term, we will end up with this term, right? Like if you take derivative with respect to Z, we get dP by dZ plus rho G sin theta. Okay, so that's why this is the piezometric pressure. So keeping that in mind, then we can write this right hand side is equal to dP star by dz equal to mu 1 by r d by dr r dvz by dr. Okay, and you can clearly see here the left hand side is only a function of r, and the right hand side is a function of the left hand side is a function of z only, and the right hand side is a function of r only. And since both of these derivatives are like a complete derivative of two separate coordinates, so this is only possible if both of these derivatives are equal to a particular constant. Okay, it's equal to is particular to a single constant. Okay, So both of these terms will be equal to a constant, okay, constant c, say. Thus we we solve this both of these equations separately, okay. So you can see that if we take this the right hand side, so dou by dou r dvz by dr will be equal to c mu into r, c by mu into r, okay. We just, if it equals c, then just take r will go up, sorry, c, then r will go up, mu will go down, okay. We again integrate this equation 1, so we get that r dvz by dr equal to c by mu r square by 2 plus c1, okay. Then again if we integrate the equation again, we get that vz by r equal to cr square by 4 mu plus c1 ln r plus c2, okay. So we have these two following boundary conditions, that r at r equal to capital R, vz equal to 0 from the no slip boundary condition, okay. Again at r equal to 0, vz equal to finite. So this can also be that comes from a symmetric boundary condition. So this can also be written in terms that dvz, sorry, dvz by dr at r equal to 0 is equal to 0, sorry, I'm sorry, is equal to 0 at r equal to 0, okay. These two are similar, okay, same. This basically implies a symmetric boundary condition, okay. So if we apply this condition in this equation, okay, you can clearly see that just wait for a while, okay, you can clearly see that since d at r equal to 0, dvz by dr equal to 0, so we can clearly see that c1 equal to 0, so we only left with capital C. So capital C and obviously c2 after the second integration. So the equation that we are left to deal with is actually only, let me write with defined equation, is only vz by r is equal to cr square by 4 mu plus c2, okay. Then now we apply our first boundary condition in this equation. So after the application of the boundary condition, we can see that we are left with this equation, okay. I can write it again. So it is vz by, so vz of r is equal to minus cr square by 4 mu into 1 minus r square by capital R square, okay. So I can clearly see that c that we have taken as c that we have initially taken as dou p by dou z, dou p star by dou z. So it clearly tells us that for the flow to move in the positive z direction, the value of the pressure gradient, piezometric pressure gradient, that is dou p star by dou z, should be negative, okay. This again a very important conclusion from the governing equations itself, that we need a negative pressure gradient to drive the flow in the positive z direction, okay. So again I will just go through this. This is the very definition of the average velocity. So I guess again I won't go through the derivation, so to save time, but it's basically the we equate the, say, like if we took a velocity, say a velocity in the case of inviscid flow field that would have sustained the same volume flow rate through this cross section, given that the flow would have been inviscid, then we take that constant value of velocity as v bar, okay, or the average velocity. So v bar into pi r square, this is radius of the pipe, so v bar into pi r square would be equal to the integration, sorry, let me just write it. So v bar into pi r square, because this is a constant velocity, it is a constant inviscid velocity profile that would have sustained the same volume flow rate in the case, the same volume flow rate in the case that is equal to the case of a viscous flow, right? Like this what I'm basically trying to say is that this inviscid velocity profile would have sustained the same volume flow rate that is being sustained by this viscid or the viscous velocity profile, okay. So that would basically be equal to, sorry, vz 2 pi r dr, right? Because this is not constant, so it is function of r, so we need to integrate that, right, to get the volume flow rate. So that is what basically we have done here. Okay, so from that we get that v bar is equal to 2 by r square integration from 0 to capital R vz r dr. So if we do this integration, we get that the average velocity is equal to minus c r square by 8 mu. Okay, so from that we can clearly see that c is equal to minus 8 mu v bar by r square, where v bar is equal to average velocity. So if we take the ratio of this average velocity and our velocity profile that we have derived from our Hagen-Poiseuille flow, so if we take the ratio, we can see that Vz by v bar is equal to 1 minus r square by capital R square. So it is actually the non-dimensional velocity profile in the case of a Hagen-Poiseuille flow. So you can clearly see that since it depends on the second order of it depends on the second power, or the second order of the square of the radius, you can clearly see that it would thus result in a parabolic velocity profile. Okay, so that's the conclusion that we get. Now we determine the wall shear stress. So again, the wall stress can be determined from this equation. So we get that the wall shear stress at r equal to small r equal to capital r equal to capital R, we see that tau wall is equal to 4 mu v by r. I am just skipping past some details so that we can save time, but again the conclusive remarks of these derivations are important, so we need to discuss that, but I am just skipping some of the definitions. You can just go through, I have written it clearly, so you just go through it. If you have any doubt, then again you can just please ask me. Okay, so again we need to determine the coefficient of friction, right? So the coefficient of friction can be defined by the ratio of the shear stress by the inertia by the by the kinetic energy, right? The kinetic energy per unit volume. Okay, so you can here again, if we take the value of this shear stress here, the wall shear stress here, tau wall, then we can see that the coefficient of friction Cf is equal to 16 by RAD. Okay, so here the coefficient of friction is actually defined or described in terms of the wall shear stress. Okay, so this is also known as the fanning friction factor. Okay, the ratio of shear stress by the kinetic energy per unit volume. Okay, so we get that the fanning friction factor is equal to 16 by RAD, right? Again we got from our previous calculation analysis that dou p star by dou z should be equal to one constant, right? Because this was the right hand side of our equation, left hand side of our equation, so that should be equal to some constant, and we again found that constant indeed is equal to minus 8 mu v bar by r square. Okay, so from this equation you can see that since dou p star by dou z is equal to one constant, and this is the first order derivative, so it clearly tells us that the variation of pressure or the piezometric pressure is linear, because the first order derivative is a constant, so the piezometric pressure varies linearly to the length of the pipe, or the linearly to the z coordinate, right, which indeed signifies the length of the pipe. So we can write this derivative, we can write it also as P out minus P star out by P star out minus P star in divided by L, because the pressure varies linearly, so the approximation for the derivative for this first order derivative is completely correct, so this is right. Okay, so since we can write this first order derivative as P star out minus P star in by L, so we can write P star out minus P star in by L will be equal to 8 mu v bar by r square. Okay, I'm sorry, just 1 minute. And again here this pressure difference, okay, P star out minus P star in, since the fluid is viscid and the flow must overcome the viscous forces to flow must overcome the viscous forces to sustain the flow, this flow field in the case of pipe flow. So the any resistance that is being provided is because of the viscous resistance, right? The viscous resistance to the flow that is being given is because of the viscosity of the flow fluid, right? That's why we can clearly tell that this, thus we can write this delta P star term, or the delta P star, because of the viscous resistance of the flow field, as a head loss, as a head loss term, HF into rho g, right? This is again absolutely correct, right? Because if we what to say, want to, like say, if we wanted to represent the loss in the pressure, right? We used to define a head loss term, right? We used to define a head loss term in the modified Bernoulli's equation, right? In an HL term, right? So let me just write it. So P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2 plus HL. So we in the modified Bernoulli's equation, we used to write a head loss term that is indeed to compensate the viscous effects of the flow field, that we usually used to ignore in the case of a in the case of Bernoulli's equation, right? But in the case of modified Bernoulli's equation, we used to incorporate the viscous effects by the use of an additional head loss term in the case of a in the what to say, in the right hand side of the Bernoulli's equation, right? So clearly this head is actually represented in the case of head per unit. This equation is represented in case of per unit head per unit mass, right? Per unit mass. So if we multiply this term multiply this term with rho g, so all these terms would be in terms of the pressure head, right? Would be in terms of pressure. So if we multiply all these terms with rho g, so we'll get P2 plus rho V2 square by 2 plus rho GZ2 plus rho GHL. So this term itself in turn represents the head loss term in terms of pressure head, right? So that's why in terms of pressure, that's why we can just equivalently write this pressure difference as HF rho g, right? HF represents the head loss due to friction. That's why if we substitute this term in this equation, we can write HF by rho g, HF into rho g by L would be equal to 8 mu V bar by R square. If we replace R by D by 2, then we get it would be equal to 32 mu V by D square. Okay. Then again we can again we can replace this velocity in the case of the ratio of the volume flow rate and the area of the pipe. So if we substitute that, we finally get that rho g HF would be equal to 128 mu QL by pi d to the power 4, or HF is equal to 128 mu QL by rho g pi d to the power 4. Then this equation is also known as the Hagen-Poiseuille equation. Okay. Then why this equation is important? It is important because the head loss due to friction, fluid friction, is represented in terms of the parameters that can easily be determined through experiments. Okay. Q can be determined by experiment by the use of Venturi meters. L is usually known to us, like we know the length of the pipe that we are using. Mu is a fluid property, so that we would know. Rho is again a fluid property that we will know before the experiment. Then G is the extension to gravity, and D is the diameter of the pipe. So all these parameters are usually known, and thus it's a very elegant way of representing the fluid friction in the case of an experimentally measurable quantity. So it becomes very easy. Like instead of representing it like this, expression is not at all wrong, but we need to, since V bar is not a quantity that we usually determine through experiments, right? We actually measure the you can say pitot tube, no? But pitot tube actually measures the velocity at a particular point in the flow field, right? It is not the average velocity in the case of a pipe flow. It's actually we derive the velocity, average velocity from the velocity profile that we have derived, right? So it's actually not the what we measure through the pitot tube. But in the case of venturimeter, we can use that venturimeter to determine the flow rate through that particular pipe, which can indeed be used to determine the head loss in that particular pipe, right? In that particular piping network. Okay, so right. Then again, HF can also be represented as a fraction of the kinetic energy head. Okay, that is what been actually done. So here V square by 2Z represents the kinetic energy head, but these two terms, right, F and L by D, since these are non-dimensional, so the dimensionality of the equation is not hampered. So these two terms acts as coefficients to as a coefficients or fractions that represents these two terms acts as coefficients that acts as a fraction that represents a fraction of the total kinetic energy head. Okay, so now if we equate these two equations, equation 2 and equation 1, if we equate these two equations, we get that F is equal to 64 mu by rho Vd, or F equal to 64 by Red. Then you can clearly see that there is a relationship between this F and the fanning friction factor, which is actually F is equal to 4CF. And there, and you can, as I told, CF was determined, like it's also related to fluid friction, because it was determined in the case of as a ratio of the wall shear stress and the kinetic energy per unit mass, or kinetic energy per unit volume. And again, this is also this friction head, this is, or the Darcy friction factor, is represented in the case of, as represented in terms of the head loss due to fluid friction, right, or the pressure head loss due to fluid friction, pressure head loss due to fluid friction. Okay, and since we know that we have to overcome the wall shear stress, and since we need to overcome a wall shear stress for the flow to be sustained, thus the flow incurs a pressure drop, and this Darcy friction factor is derived from this perspective, from the pressure drop perspective, the head loss in the pressure. And again, the fanning friction factor is derived or determined from the wall shear stress perspective. So that's why, since these two physical phenomena are extremely interconnected, because they are, bidirectionally related, like there is a pressure drop because of wall shear stress. So I won't say bidirectional, I must say unidirectionally related, because there is a pressure drop because of the wall shear stress. And since these two physical phenomena are related, that's why these mathematical expressions or mathematical derivations of the same phenomenon, this is a friction factor, are thus related, the Darcy's friction factor and the fanning friction factor. Okay, so there is one more important mathematical definition, that is power required to overcome the head loss. So usually we use pipes, we used additional instruments or additional machineries to overcome this head loss. Like obviously, if we just let the flow pipe, if we let only the pressure gradient to sustain our pipe flow, then it's very difficult to sustain the pipe flow, because the frictional losses in the pipe flow are so large that the flow it's very difficult to sustain the same flow rate throughout the length of the pipe, right? It's very difficult. So I won't say throughout the length of the pipe, like as the length of the pipe increases, it's very difficult to sustain the same flow rate, I would say that. Thus, in order to overcome this vast shear stress, these shear stresses or pressure losses, we use some additional equipments to boost up this pressure head, which in turn are known as pumps. So these pumps are used to supply hydraulic energy to the fluid to overcome these shear stresses, and thus the power required to overcome these head loss or shear stresses are represented in terms of the power is equal to del P star into Q, where del P star is equal to rho G HF, right? And here del P star, I need to emphasize that del P star is not only the pressure difference, but it is actually the piezometric pressure difference. Okay, so sometimes we may, like, if there's an inclination in the pipe, we may and the value of the pressure are given at the two ends, like sometimes we may get confused and we only use those two values, but instead we should also keep in mind the piezometric head or the potential energy difference that is basically being denoted by the difference in the height of these 2 points. So that also need to be considered. Okay, so that's why it is a piezometric pressure difference and not the pressure difference itself. Okay, or the, I must say, the static pressure difference itself. So actually the piezometric pressure. Okay, so just since we are short of time, I will just skip past this section. So this section basically emphasize the fact that which I briefly discussed in the beginning of the session, that since the analytical solution of the turbulent flows through pipe not available, we usually resort to experimenting develop correlations for this purpose. Okay, and some of the conclusions that we get from the dimension analysis is that the ratio of the pressure difference, or here it's mentioned pressure difference, so I can also say as the piezometric pressure difference by the kinetic energy head is actually a function of the Reynolds number, the ratio of length by diameter, and the ratio of the surface roughness epsilon by the diameter. Okay, so this is a new term again, so I will write it. So here E is equal to the surface roughness. Okay, so in the case of fully developed flow, the flow becomes independent of this ratio becomes independent of the length of the pipe. So that's why this ratio comes out as a function. So okay, so del P by half rho V square is equal to L by D into a function of rho V into a function of the Reynolds number and the surface roughness. Okay, and this friction factor is known as the Darcy's friction factor in the case of turbulent flow also. Okay, see, this is important to know that in the case of this expression for Darcy friction factor, okay, there is HF is equal to FLV square by 2GD is valid for both turbulent and laminar flows. Okay, it's very important, and also the flow should be fully developed. Okay, that's why this dependence on length of the pipe goes out in the case of a fully developed flow. So that's why it becomes quite simple. Okay, so here you can see that then F is only a function of Reynolds number and the ratio of the surface roughness and the diameter of the pipe. Okay, so if we equate again, if we just play with this equation, like the values, you can represent HF is equal to F V average square by 2G into L by D, which is exactly the same result that we got in the while we were discussing for flow through the laminar flow through pipes, right? It was exactly the same. So the expression remains the same and applicability also remains the same, but the differences arise in the manner in which the value of F is determined. Okay, this is a bit tricky in the case of turbulent flows. In the case of laminar flows, it's very simple. We have very simple analytical conclusion that F is equal to 64 by RE. Okay, this is a very simple result for laminar flow. But for turbulent flow, it is very difficult to actually determine the value of F, because it's is function of both the Reynolds number and the surface roughness ratio of the surface roughness and the diameter. Okay, for simplicity I will just say f is a function of both surface roughness and the Reynolds number. Okay, so there again were various researchers who worked upon it, developed their own relations, as one of the relations is shown here. It is the Colebrook formula for determining f, this friction, Darcy's friction factor. So this equation is again valid for Reynolds number above 4000, as I told, right? Not 2301. Right? They also know the significance of the transition region, so they have defined a value of Reynolds number that is well beyond the transition region. So it is this beyond 4000, the flow can be taken to be fully turbulent. So Colebrook said that this equation is valid for all values of Reynolds number beyond 4000. So this is actually very standard equation that is being used in for most of the analysis, turbulent flow analysis in pipes. So this is a very important reason. But the tricky part of the equation lies in the fact that this is not actually an explicit expression. This equation is actually implicitly dependent on f, okay, the friction factor. So we use different iterative methods or computer codes to solve this equation for the given value of surface roughness ratio and the Reynolds number. Okay, then again there's different relation for flow to smooth pipes, so I guess I will just not emphasize it upon much. Okay, let's just go to some examples. I guess that will help us in clearing our concepts a lot. Okay, so these are examples that this is an example that is being taken by Professor Gupta in his lecture. So I will just go through it. So I hope I am able to clear the doubts. Okay, a fireman with an 8 cm diameter hose directs a jet of water at 60 degrees to the horizontal so as to reach the fire at 10 meter above the ground. Okay, if the nozzle and the hose diameter are the same and the length of the hose is 30 meter, what should be the head developed by the pump? Okay, this is what we need to determine. The head developed by the pump. Like there is a additional pump that is being used to overcome the head frictional losses. So what is the head or additional hydraulic energy that needs to be provided in this hose so as that this fluid reaches the fire that needs to be extinguished. Okay, so the geometry is defined here. So the fireman directs the pump at an angle of 60 degrees from the horizontal, so which has to reach a fire that is 10 meter above the ground. Okay, so we need to find the velocity through the hose. Okay, and one more thing, we need the equivalent roughness of the hose is given by 0.0008 meter. Okay, and we also assume that there is no reduction in the cross section of the nozzle. Okay, this is already given the question that nozzle and the hose diameter are same. Okay, so to determine the to start with the problem, we need to determine the velocity of the pipe. Okay, there's the first thing that we need to determine, because that will again help us in determining the Reynolds number, which we again be used. Like if the Reynolds number is known, then we can with the help of the Reynolds number and the surface roughness, like since we need to know the head loss, I'll just give you a simple algorithm. Okay, since you need to find the head loss, okay, you need to get the friction factor. Okay, then again this friction factor is dependent on both RED and epsilon by D. Okay, then again to determine RED, since the dimension of the pipe is given, we need to determine the velocity of the flow. Okay, so this is a simple algorithm. So in order to determine the head loss, we need to get the friction factor. To get the friction factor, we need to get a Reynolds number and the epsilon, the ratio of surface roughness. This is already given, so we need to determine the Reynolds number. Again, this Reynolds number can be determined by if we know the diameter of the pipe and the velocity. Since diameter is already given, we need to determine the velocity of the flow in the pipe. Okay, so this is the algorithm that will usually flow in such kind of problems. Okay, so we need to determine the velocity of pipe, velocity of the flow in the hose. Okay, so we can determine it. We can determine the velocity of the jet. Why? Because it's clearly told that the velocity of the dimension of nozzle and the hose remains the same. So there is no increase in the velocity of the jet, which comes out of the nozzle. Okay, since the diameter or dimension of the hose and the nozzle remains the same. So there is no area reduction, so there is no increment in the velocity from because of the continuity equation. Okay, so we apply the Bernoulli's equation at the nozzle exit and the highest point okay, where the water reaches. Okay, so we get that at the nozzle exit, velocity of the water would be the velocity of jet, so it is equal to Vj. Okay, so Vj square by 2g plus P ATM by rho g. If we take it as a datum, so z is 0, then that would be equal to Vj by 2 whole square by 2g plus P ATM by rho g plus 10. Okay, we can take that since pressure at both here and here is atmospheric pressure, so these two terms will go out. Okay, z equal to 0 in this case, so since it is a relation of 10, then z is equal to 10 in this case. Okay, the tricky part is why velocity at this point is equal to half of the velocity of the jet. Okay, it's because it comes from the concept of projectile motion that I have deduced, like that I have deduced from like I can tell. So it comes from the concept of projectile motion. Okay, so at the maximum height, like if we assume the motion of this jet as a projectile motion, I may be wrong, but this is how I have thought that it could be done. So if we take at maximum height, since if we take this concept, if we take it similar to a projectile motion, then at maximum height the y component of the velocity is equal to 0. Okay, so only the x component of velocity remains at this point. At the highest point, y component of velocity is 0. So that's the x component of velocity keeps on driving the flow, right? So Vj is equal to Vjx at the highest point. Okay, since Vj is equal to Vj cos theta, so we can tell that Vj is equal to Vj cos 60 degree. Since cos 60 degree is half 0.5, so we can tell that Vj is equal to Vj by 2 at the highest point. Okay, let me just write it. Okay, so from that, if we solve this equation, we get that Vj is equal to 16.17 meter per second, right? So from that, as I told, the same algorithm, since velocity is known, now we can determine the Reynolds number, since diameter is also given. So from the value of this Reynolds number and the surface roughness, we can now look into the Moody's chart. Like I guess we have this has been discussed in Professor Gupta's lecture. This is a very standard chart that is being used to determine the value of the friction factor. Okay, in the case of turbulent flow. So because in the case of laminar flow, Reynolds number is known, we can easily determine the friction factor. So this chart, Moody's chart was fundamentally developed to determine the value of friction factor in the case of turbulent flows. Okay, so since Reynolds number is known and the friction factor is known, from the Moody's chart we get that F is equal to 0.038. Okay, then we substitute the value of F in this equation, then we get that the head loss would be equal to 189.9 meter. Okay, so in order to determine the total head loss, a additional head HS needs to be developed by the pump to apply the so that the flow can overcome the viscous stresses, right? That's why we apply the Bernoulli's equation between the pump inlet and the nozzle exit. Okay, let's go back to the diagram. So we apply the Bernoulli's equation at the pump inlet and the nozzle exit. Okay, here. So we get that. Why you are applying? Again, this is a very important thing. Like because here also it's strictly given that P is equal to P ATM, and here also P is equal to P ATM. So the pressure terms will go out, right? Again, you need to apply it because all the energy head that is being applied is being applied from this junction, right? From this junction to this junction. But here we do not know the pressure. Here we know the pressure, so we can elegantly apply the Bernoulli's equation between these 2 points, right? And so that's why applying Bernoulli's equation between these 2 points, we get that P ATM by rho g plus V square by 2g plus Z in is equal to P ATM by rho g plus J square by 2g plus Z out plus HL, that is the head loss due to friction plus HS, that is the additional head that is being applied by the pump. Okay, so both pressure will go out, since pressure is equal to P ATM. V square by 2G would be equal to 0. Why? Because it is given in the question that the velocity at the reservoir is 0. So V is equal to 0. Z in and Z out is because they are both at the same elevation, so this terms will go out. So we are left with minus HS is equal to Vj square by 2G plus HL. Why this is minus HS? Because it signifies the fact that an additional energy has to be applied from outside, like the additional energy has to be applied through in this system, so that the flow could overcome this frictional losses. Okay, so this negative sign emphasizes the fact that there is an additional energy being applied in the system. Okay, so if we solve that, we get that Vj square by Vj is equal to 16.17 meter per second. So Vj square by 2G plus 189.9, we get that minus HS is equal to 202.3 meters. So this is the additional head that needs to be applied in the flow field, so that the flow can reach to the to this elevation. Okay, to this additional elevation of 10 meter. Okay, right. Okay, so there is again one more concept, important concept in this thing that we need to take into consideration. That is, we can clearly see that application of this much amount of head, like, is very difficult or very costly. Like we cannot apply so much head, like so much head is required, or pressure, or additional head or pressure head is required, so that we can just supply water to a height of 10 meter, right? So it seems contradictory, right? We are supplying an additional height of 203.2 meters so that we can pump this liquid to a height of 10 meter, right? So it seems quite unsatisfactory, I must say, right? So we can clearly see that this additional head that is being that was there was because of the fact that the velocity in the pipe was too high, right? The velocity of pipe was too high. So we why? Because see, this head, you can clearly see that the most of the component, or the most of the part of this 202.3 meter comes from this term, right? 189.9 meter, and you can clearly see that this is high because of the fact that the velocity at the hose or the pipe is very high, 16.17 meter per second. This is the velocity of the pipe that we need to supply in the pipe. And since this is high, this depends on a power of 2 square, so this exponentially increases the required head in the pump, right? It exponentially increases the head required to overcome the frictional losses. So what we can ideally do is, since we cannot reduce the length of the pipe, this is beyond our control, right? This is beyond our control. And also dimension of pipe, these geometrical variations are usually difficult to be done, right? Because these come in standard manufacture, these are manufactured in some standard measurements, so this cannot be usually altered. So what we can ideally do is, we can change this velocity, and since it's dependent on the square, it's dependent on the power of 2, reduction in the value of the velocity would exponentially decrease the head loss in the pipe, right? Which would in turn reduce the additional power requirement through pump. Okay, so we can see that the first task is to reduce the velocity of the fluid in the hose, okay, in the pipe. But again, we cannot reduce the velocity of the pipe at the exit, velocity of flow at the exit, because we need the velocity of 16.17 meter per second, so that the fluid can reach at the height of 10 meter, right? So we cannot reduce this velocity. So the only thing that can be done is, we can apply a nozzle at the exit of the pipe, so that even with a lower velocity in the pipe, the area reduction would result in a higher velocity, or comparatively higher velocity than the velocity of flow at the hose, which would be satisfactory, which will give us a velocity of 16.17 meter per second, which in turn would lead the fluid to reach to the destined height, or it is the destined height of 10 meter, so that the fire can be extinguished. Okay, so the best way to deal with such scenario is that we can apply a nozzle. Okay, So if we take a nozzle of 2.5 centimeter diameter, okay, then the velocity at the hose would be given by 16.17 into 0.025 by 0.08 whole square, which will give us velocity at the hose as 1.58 meter per second. Okay, so sorry. Right. So you can clearly see that the use of a nozzle drastically reduces the velocity of the fluid, the velocity required of the fluid in the pipe. Right. So it is now 1.5 meter per second. Now, if we determine Reynolds number with this, so we can get that the Reynolds number of the pipe is now Reynolds number of the flow in the pipe is 1.26 into 10 to the power 5. Now again the surface roughness remains unchanged, so epsilon by d is 0.001. So from these values of Reynolds number and surface roughness, we get that F is equal to 0.038. Okay, then HF again is equal to 1.81 meters. See, there is a very drastic reduction in the head loss, that is loss in head in the pipe. Okay, this is drastic loss because of the reduction in the velocity, which is in turn attained by the use of a nozzle at the exit of the hose. Okay, just a very simple tweak, just a very simple design tweak in the in this problem has resulted in a drastic change in the requirement of the head, right, or the pressure loss, or the head loss in pressure, right, pressure head loss, right. That's why it's a very, like, or to say, very beautiful conclusion that we get. Like, why usually you also see that usually if you see some firefighting videos or firefighting fire rescue operations, you will see that the this pipe that they use to eject the fluid to the liquid to the required destination, you see that this usually has a nozzle at the exit, so that they could release the water at higher velocity so that it reaches the required height. But again, this velocity, the velocity of the fluid or water and the pipe is comparatively lower than the velocity of the jet that is being ejected from the nozzle exit, right. And this low velocity requirement in the pipe thus results in a very low head loss in the pipe, low frictional loss in the pipe, and thus a very comparatively very low pumping power is required to eject the fluid from a lower elevation to a higher elevation, so that the fire can be extinguished. Okay, so that's a very important conclusion that we get. That's why I found this problem very interesting from my side also, personally also, right. So we get that, so we apply the same equation. So minus H is equal to Vj square by 2g plus Hl. So Vj would remain the same because it is the velocity of the jet, so it is 16.17 square plus 2 into 9.81 plus 1.81 is, we get that the required pumping power is 15.13 meter, right, which is drastically low compared to 2.03. So this is a very huge difference, right. So you can now see that the main contribution is from this part, the velocity jet. Okay, the power required to eject the velocity from 0 elevation to 10 meters. So that's the beauty of engineering. Like, simple tweaks in the design can result to drastic modifications or designs, drastic modifications in the flow parameters. Okay, so this is actually the Moody's diagram. So this is very simple. I will just tell you one example. So see, our F, our frictional factor, is solely the function of Reynolds number and surface roughness ratio. Okay, epsilon by d. Now see, in the case of laminar flow, you can clearly see that this is actually a straight line. It's actually only a straight line because it depends on 1 by Re. It depends on the inverse of Reynolds number. Okay, so as the Reynolds number increases, the value of friction factor decreases. So it varies linearly. Okay. So I guess I am wrong in that sense, but for very low values of Reynolds number, this curve follows a linear pattern, because 1 by x curve actually goes varies as this. So I'm sorry, but for low value of Reynolds number, this trend is almost linear, okay, and thus this has value of friction factor has no dependence on the value of surface roughness, okay. So here in this diagram, in this chart, let me just introduce. So right hand side, this term, this scale or this coordinate represents the value of friction factor, okay, F. That usually is the required value. The x coordinate is the Reynolds number, okay. That can be usually found out if the velocity of the flow field is given or the volume flow rate is given along with the dimensions of the pipe, okay. Then the relative surface roughness, okay. I was telling the surface roughness ratio is actually relative surface roughness, so I'm sorry for that. So this coordinate represents the relative surface roughness, okay, relative pipe roughness, okay, epsilon by d. So what for the determination of the friction factor in the case of turbulent flows, we first of all we need to find the value of the relative surface roughness epsilon by d and the Reynolds number, okay. So that we need to determine. So that is the most tricky part, how to determine the Reynolds number and how to get the relative surface roughness, okay. This is for most of the problems, this is straightforward, because either this will be given to you straightforward, or you will be given the particular material of the pipe, so that you can get the standard value of the surface roughness by its material, okay. So that can be done. So this is straightforward, value of this can be determined easily. Tricky part is the Reynolds number. So sometimes what happens is that both the volume flow rate or the diameter is not given, right? So what happens is that sometimes it is difficult, that the problems it is modeled to design in such a way that you cannot determine the Reynolds number straight away. So you need to find some iterative methods to find the Reynolds number, okay. So that we'll see some problems how we can find it. But the thing is that you need to find a Reynolds number. So this is the most tricky part. You need to find a Reynolds number. So once you get both the Reynolds number and the surface roughness ratio, then you can find the Fanning's friction factor, okay. So say we got that our relative surface roughness is 0.002, okay. Just take this value, okay. Then again, like if we want to take that, if we have the Reynolds number, now we found that the Reynolds number of our flow field is 10 to the power 5, okay. So if we go from here, so 0.002, here this is the line, okay, this is the line. So now for 10 to the power 5, we go from here, so 10 to the power 5, right here at this point, right. So if we go here now, so the Fanning's friction factor in this case would be equal to say 0.0024, okay. Sorry, 0.024. So this is how the Fanning's friction is being determined, okay. So another catch is that, like if say the Reynolds number, as I told, sometimes it may happen that the Reynolds number cannot be explicitly determined, okay. So you need to find some different tricks or methods to find a Reynolds number. So we then take the result of, like we take the help of iterative methods. So we need to guess the Reynolds number, okay. So a standard a very wise method or a very intelligent way of doing that is to consider a fully turbulent flow field, okay. Like if we know the value of surface roughness, like you can clearly see that as the Reynolds number increases, like say not the lower values of surface roughness, but say for the higher values of surface roughness, say I would say from 0.001, say this region, okay. Sorry, say from this region. So you can see that beyond 10 to the power 6, okay. Now 10 to the power 6 per pipe flow, it means that the flow is absolutely turbulent. It is highly turbulent, okay. You cannot argue that it is laminar. So it is fully turbulent, no questions asked, okay. So if we assume that, now say the flow is highly turbulent, fully turbulent, I assume that the value of Reynolds number is 10 to the power 6. Okay, so it basically means that now, since the value of Reynolds number is 10 to the power 6, the friction factors now are just, what to say, like beyond this region, there's a you can sorry. So we can take an assumption that now say it's 10 to the power 6. Now we got, so if we had a value of say 0.002 again, now I take a guess that the value of Reynolds number is 10 to the power 6. Okay, then it's very easy, like if it is here, so you can easily determine that the value of surface roughness will be around say 0.0023. Okay, so what I basically mean to say is that for the fully turbulent regions, the variation in the, what to say, the friction factor becomes independent of the Reynolds number. Okay, you can clearly see that for high Reynolds number, these are straight lines. Okay, beyond 10 to the power 6, for most other cases, for like values higher than 0.001, most of these lines are straight lines. So you can just the determination. Sorry, I'm sorry, it's disconnected. Okay, so okay, I'm sorry, so the screen got disconnected. So okay, sorry for the interruption from my part. Okay, so yes, so for higher values of Reynolds number, you can clearly see that the friction factor becomes independent of the Reynolds number. So it seems like it only depends on the relative surface roughness, right? So it becomes quite simple. It, like, the analysis becomes a bit simple. Like if you choose now here, say Reynolds number 10 to the power 5, then you need to again go to the curved part, then again take the scale. So it becomes quite tedious. So like now, if we had an option to make some assumption, so we'll take one that is simpler for us to analyze, right? So, and that is a region where it becomes quite independent of Reynolds number. So that is what we do. We take high value of Reynolds number. Say now we won't take 20% because it becomes quite, like, what to say, a bit too far from the actual flow, right? 10 to the power 7 is not what we usually get for pipe flows, right? So it becomes quite there. But say as it is distinctly demarcated by this dotted line, so I don't know is it available for all the textbooks, so I'm sorry, I do not know that. But beyond this line, you can see that the flow is completely turbulent, right? So we can take and beyond this, you can see that the flow here, the flow becomes independent of the Reynolds number, right? That is what this line is signifying, as I mentioned. So we take the values of say if it is 0.02, we take a value here around say 10 to the power 4 into 10 to the power 5, such that the flow is independent of Reynolds number. Now I will take a guess, find the value of friction factor, then see if it gives me the same Reynolds number, right? Like once I guess, then if the value of friction factor is known, then I can, from that value of friction factor, I can now determine the value of Reynolds number. Now I will see if this Reynolds number matches with the Reynolds number that I guessed. So if it doesn't, I will repeat the same calculation and repeat the calculation until I get convergence in the value of Reynolds number. Okay. So once I get the convergence in the value of Reynolds number, I can determine the value of the velocity or diameter, whatever is not given, then just carry forward my calculation. Okay. So this is the method that we usually use. So this is all about Moody's diagram. So it's very important part of this analysis. So we will time and time again resort to Moody's diagram for analysis of friction factor. But the trick is, first of all, we need to find the relative surface roughness ratio, surface roughness then the Reynolds number, then the friction factor. Then from friction factor we get the pressure pressure head loss. This is what usually the pattern of the question is in this kind of examples. Okay. So okay, I guess I'll skip this example, maximum power. I guess this is can be done. So this is again interesting. Okay. The question is, obtain the rate of flow of water carried by a cast iron pipe. Diameter is 10 centimeter and length is 40 meter. When the applied head difference across it is 2 meter. Okay. See, this again an interesting question. See, here they have not mentioned the value of the relative surface roughness. Instead, they have mentioned the material. So in the case of competitive exams like GATE or ESC, I will say that most of the times you will be explicitly given the value of the surface roughness. Okay, the equivalent surface roughness or the average surface roughness, as they say. But as an engineer or as a fluid mechanics student, it's usually like not bad. I'm not saying necessary, but it's usually not bad to have some idea of how the surface roughness would vary from material to material. Like it's not compulsory, but like if at all, like you are now in future, if you become a engineer that deals with pipe flows all the time, no. So that in that case, an idea of knowing the value of the relative surface roughness, or sorry, the equivalent surface roughness or the average surface roughness for different materials becomes quite handy, right? You need not to look into the books all the time. Okay, so that's fine, but still I'm just saying. So if you know that, then that's the problem becomes simpler. Okay, but the thing is that the question is modeled in such a way that you need to know the value of the relative surface roughness in the case of a cast iron pipe. Okay, again the trick in this question is that here the velocity is not given. Since the velocity is not given, you cannot determine the Reynolds number, right? Diameter is given. See, either the diameter or the velocity would not be given. So in that case, we need to take the help of some iterative methods to find the Reynolds number. Okay, because since if both are given, the Reynolds number can easily be determined. So once Reynolds number is determined, you can, and the surface roughness knows, then you can easily determine the friction factor. So the question is solvable. It's straightforward. But the trick comes in the picture that in this picture is that now the either the velocity or the diameter is not given. So we need to take the help of some iterative methods to find the value of the velocity or the diameter, whichever is not given. Okay, so that we can get the Reynolds number. Okay, it's actually the other way around. We get the Reynolds number, then we determine the value of the velocity or the diameter. Okay, so let's get into it. So velocity is not given, so that's the trick. Okay, so that makes the problem quite difficult compared to the previous case. It's not that straightforward now. But here again you can see the head loss is given. Okay, so we need to determine the rate of flow now. Q, we need to determine Q. Okay. Now, okay. So we know that HL is equal to FL V square by 2GD. Okay. So it gives that V is equal to 2GD HL by FL. Okay. Now we just substitute the value of the parameters that we already know. HL is equal to D is equal to 0.1, L equal to 40. So we get that V is equal to 0.313 root F. Okay. Again, epsilon for a cast iron pipe is 0.15 mm. Okay. So epsilon by D would be equal to 0.0015. Okay. Now epsilon by D is known, but Reynolds number we do not know. So as I told, what we do is that we take a guess of Reynolds number. That is usually in the case of a fully turbulent flow regime, that there's usually the standard way of solving the problem. That it helps in faster convergence. Okay. So we assume the flow to be fully turbulent so that F can be estimated without knowing the value of the Reynolds number. Okay. So because it's simple, because at fully turbulent flow it becomes independent of Reynolds number, right? So just by knowing the value of the relative surface roughness, we can determine the value of friction factor. So from Umri's chart, we get that for the value of 0.0015, we get that F is equal to 0.021. Okay. So from this value we can calculate the value of V using this equation. Okay, using this equation. So from that we get that, from that we will get a value of Reynolds number, because since V is known, diameter is known, we can get the value of Reynolds number. Now from that calculated value of Reynolds number and surface roughness, this would remain unchanged, right? So this is what we get from using the value of velocity that we got for our initial guess, right? So once we know the value of this Reynolds number, this guess, and the relative surface roughness, now we can determine the value of F from the Colebrook calculator. Okay, so this is a method that is being used by in Professor Gupta's lecture. Like there's a link given for the value of, for the calculation of value of F once you know the value of Reynolds number and relative surface roughness. So you can take the help of that also. So if you are taking the help of that method, so from that Colebrook calculator we get that F is equal to 0.0027. Okay, so now we repeat the same analysis. We again use this value of F now to determine the velocity value of velocity from this equation, right? That we got from here. Okay, that we got here, right? So we again determine the value of velocity. We get that velocity is equal to 2.08 meter per second. From this we determine the value of Reynolds number now. From that we get the value of Reynolds number as 207745. Now from this value of Reynolds number and the value of relative surface roughness, that is epsilon by d, we again determine the value of F from the Colebrook calculator. We again get the F is equal to 0.0028. Now again we use this, since again like this can be quite satisfactory. Like I'm not saying it is wrong at all. Like you can conclude the result here also. But again, if you want more higher accuracy, like then you can do one more iteration, right? There is no harm in that. So for this value of F, again you determine the value of velocity, then again use this to determine the Reynolds number, then from the Reynolds number and the relative surface roughness you determine the value of F again. So now we see that these two are identically same, right? So you can say that the velocity is now, the velocity would be equal to 2.07 meter per second. So once velocity is known, you can easily determine the value of volume flow rate, right? Because a diameter is given, so it's quite simple. Okay, now we look into again one of very important concept, that is head losses in pipes. Okay, I'll just go through it. Since the flow patterns to most of these fittings are too complex to be modeled analytically, the head loss are specified as experimentally determined correlations. Okay, so since like okay, just help you with the diagram. Okay, so for fully developed turbulent flows, the head loss for a fitting is usually specified as a fraction or a multiple of the kinetic energy head. Okay, the non-dimensional factors K is determined as loss coefficient and depends in general on geometry of the fitting and the Reynolds number. Okay, so what is trying to tell is that, like, if there is a sudden expansion or contraction in the pipe, like which is usually the case, like we usually tend to fix pipes of different diameters as per our requirement, right? So that is usually being done. So this kind of arrangement, arrangements usually results in pressure losses, right? So just 1 minute. So this kind of arrangements usually results in pressure losses. Why? Because of the flow separation, right? Since there is a sudden expansion or contraction, this results in flow separation. This will result in flow circulations in these regions, which thus results in energy losses, right? This is what we have shown in show in the case of venturimeter, right? Why there is a gradual increment in the diverging section in the case of venturimeter. That is to reduce the pressure losses and energy losses, right? Or the pump, or specifically in the case of pipe fittings, this kind of arrangement will result in a higher requirement of pumping power, right? So we want to avoid that. So in order to avoid that, we need to know how the inclusion of such fittings or arrangements would result in additional losses, right? And we want to minimize it. So there must be a way to characterize the losses, right? So since again as it is mentioned that these kind of losses are usually very hard to be determined or treated analytically, so these are usually determined by the use of experimental methods, right? Empirical relations, which in turn gives some values of which in turn represents these losses as a fraction of the kinetic energy head loss, right? So that is what is mentioned here, right? Like this ratio FL by D into V square 2G is actually the head loss due to friction, right? But these coefficients, okay, again these values are actually some values of some certain constant values, say 1, 2, 3, like some constant values, which again represents some fraction or multiple of the kinetic energy head, right? Which thus helps us, which again it cannot be an exact value, but helps us in giving an approximate value of the losses that has incurred because of this sudden expansion or contraction in the pipes. Or again there can be defined as losses can also be due to some elbows that are being used to join pipes in right angles or different angles, right? So there will be some elbows that are being used to connect pipes. So this kind of arrangement also results in the losses, right? Also there can be valves, right? The valves that is being used to regulate the flow rate. So again such valves can also result in some losses, right? So these losses are usually termed as minor losses in the flow field, but you will see that, like, contradictory enough, like in most of the cases these losses, right, losses due to fittings, bends or valves are usually comparatively higher compared to the head loss due to friction, right? So this is a contradictory case this is one of the contradictory examples in the case of fluid mechanics definitions, but this is what that has been used from the time from the time of its inception. Like it is being defined as minor losses from the researchers or scientists who have derived those. So this is a trend that we usually follow in order to respect them, but I'm just saying the contradictory characteristics of these losses. Like it might be usually sometimes higher than the frictional losses, but still these are represented as minor losses, so we will name them as minor losses. Okay, so I will take one example here. Okay, so here we need to determine the value of volume flow rate. Okay, so it is just told that the fluid is being transferred from a higher elevation to a lower elevation by the help of a piping network, which by help of pipe which has a 2 globe valves, okay, 2 90-degree elbows, right? And then again, since this flow enters a pipe, so there must be loss at this point, and again this as it exits this and enters the pipe from the reservoir, then again exits the pipe from this point, so there must be losses at these points also. So we need to consider these losses as well, right? And this is located at an elevation of 40 meter from a datum, from a particular datum, and this is located at a height of 5 meter from a particular datum. Okay, so as I told, these values again are usually, like if at all it will be given, it will have some certain values that will be explicitly given in the question, but you need to know how to determine, how to apply those values in the question, right, in the particular problem, right? So that's why I'm dealing with this example. So we apply Bernoulli's equation between points 1 and 2. Okay, the modified Bernoulli's equation, right? Since we know Bernoulli's equation is explicitly for inviscid flow, but in order to account for the head losses due to viscous effects, we take the help of modified Bernoulli's equation. So from that we get that if we apply the Bernoulli's equation between point 1 and 2, so we can see that at point 1 and point 2 P is equal to P ATM, so this both will go out. V1 square by V1 and V2 would be go out because both velocity at point 1 and point 2 are 0. Then again Z1 and Z2 would remain, and the HL term would remain. Okay, so we get that 40 is equal to 5 plus HL, so HL is equal to 35 meter. This is basically the total head loss between point 1 and point 2. Okay, but since this can not only be because of frictional losses, because there are various fittings and arrangement in the pipe, so we would have frictional losses as well as losses, minor losses due to these fittings. Okay, now this is this value of this coefficients we need to determine from the experimental results. Okay, so for N10 that is well rounded, the value of K is 0.09. Okay, and now since again there are two elbows in the pipe, as you can clearly see here, there are two elbows, we need to take this into account. So for the value of two elbows, we get K is equal to 2 into 0.7, where 0.7 is the value of this coefficient for a single elbow, 90-degree elbow. Okay, for a global valve, for fully open valve, this loss is equal to 10. So valves will have very high losses. So that's why I mentioned valve. Okay, so there will be high losses in the case of a valve, if at all it is there in the case of a pipe, in the case of a piping network. Okay, there are again two, so there's a very high losses because of valves. These two valves. Again, there's an exit, because this exit again from the pipe to the second reservoir. So the second pipe, fluid exits from this pipe to the second reservoir. So this again some particular value of the exit, the particular value of the coefficient. So what we do is we sum up all these values. So from that we get that sum of all K is equal to 22.49. So again we get that sum of all K is 22.49. So we can directly write it here. Then the value of surface roughness is given 0.15 mm, since it's cast iron, I guess, if I'm not wrong. Okay, it is already given. So sorry, it's for galvanized iron pipe. I'm sorry, GI is galvanized iron pipe. Epsilon by D is 0.003. Okay, so here both since V is not given, we need to determine the velocity. Just 1 minute. Okay. Oh, I'm sorry again. The screen got disconnected, so I'll just reconnect it. Okay, so just 1 minute. Okay. Since the velocity is not given, it's difficult to determine a Reynolds number. It's not possible to determine a Reynolds number. So we need to again take the help of this iterative method. I mean to guess the value of the Reynolds number, right? So for the value for epsilon by D is 0.003, we take initial guess of F is equal to 0.0026. Okay. So again it is usually taken for a fully turbulent region. So F is equal to 0.026. From that we again determine the value of velocity by substituting the value of F in this equation. We determine the value of the velocity. From that we get the value of Reynolds number. Then again from the Colebrook calculator we get the value of F is equal to 0.0273. Okay. Once we get that, we substitute this value of F again in this equation, find the value of V here, again get the Reynolds number, then again determine the value of the F. Since we see there's no difference in the value of the friction factor, we can tell that the value of velocity is 2.284. So from that we get the volume flow rate is equal to 4.50 into 10⁻³ meter cube per second. Okay, so that's all for piping head loss through pipes. Now we look into one of the very important concepts. Okay, that's piping networks. Okay, so there is basically pipes connected in series and parallel connections. Okay, so multi-pipe flow networks are common in water supply and sewage networks, and these are solved by recognizing and exploiting their similarity with electrical networks. Okay, so we know that in electrical circuits there are both series and parallel connections. So comparing these piping networks to the electrical circuits, we can similarly devise some relations and then determine the value of the required parameters. This is usually the head loss and the volume flow rate. Okay, so in the case of pipes in series, the key remarks to be taken into account is that for pipes connected in series, the volume flow rate through all the pipes remain the same. Okay, that's the first conclusive remark. The second is that the net head loss between this connection of pipes, like if there is head loss between point 1 and point 2, the net head loss between this connection of pipes would be the head loss between the individual. The net head loss would be equal to the sum of the head loss in these individual pipes. Okay, since in this diagram, if there are 3 pipes, the net head loss between these 2 points 1 and 2 would be HFA plus HFB plus HFC. That is the sum of head loss in all the 3 pipes. Okay, so if we again ignore the effect of sudden expansion and sudden contraction that usually occurs here, there is a sudden expansion here, there is a sudden contraction here. If we ignore this effect, you can write that HF is equal to this, right? I will not read out, like just it is very simple and self-explanatory. Then if we want to remove velocity in from this equation, we can represent it in terms of volume flow rate. So we can write HF is equal to this, right? So like now again, if the pipe is made of same material, we can consider that the frictional okay, I am sorry, this is actually not possible. So because friction factor would depend on other parameters, so this approximation is not possible, so I am sorry for that. Okay, so now this is what we get, right? So this is the conclusive remark that we get. So let me just draw it. So, okay, now if say we want, say like if instead of these 3 pipes, like say there are 3 pipes in the junction, right, which again comes with their own complications, right? There are some losses due to sudden expansion, contractions, and it might happen that they are consuming more space than required, so we want to minimize that space because of different sizes of diameters of pipes. So we want to minimize it to a normalized value of the diameter, right? So what happened that instead of using pipes of different diameters or different lengths in this series connection, what we want to try is that we want to replace this junction with an equivalent pipe of say an equivalent length and equivalent diameter. Okay, so that is what we need to we want to find, right? So in order to do that, so if we did since the head loss remains the same, like so now what we do is that we represent this head loss HF as an in terms of equivalent values of a particular normalized pipe. Okay, single pipe. So say if Fe is the value of the friction factor in that normalized length or dimensional pipe, L is the length of the equivalent length of the pipe, and D is the equivalent length of the diameter of the pipe, and V is the velocity of that velocity through that pipe. Okay, so if we represent V in terms of the volume flow rate, then we get that this with HF will be equal to 8 by G pi square FELE d to the power 5 into Q square. And since Q remains same for all the pipes, you can tell that Fe by LE d e to the power 5 would be equal to the sum of all this expression for all the individual pipes. Okay, so this is again some important conclusive expressions for pipes in series. So again comparing with a electrical circuit, this series connection of pipes can be considered to be a series connection of resistances, where the volume flow rate can be taken to be equivalent as the electrical current, and the potential difference between this circuit can be actually taken as the head difference between the two ends of the pipes. Okay. Similar to that, now we take in consideration the case of pipes in parallel connection. So here again the conclusive remark is that the head loss between the two pipes, okay, or any n number of pipes that are being connected, but in this diagram there are two pipes, so we can say that HFA would be equal to HFB would be equal to HF. There is the equivalent head loss between these 2 points. So the head loss between these two pipes would remain the same. Okay, and again Q there is a volume flow rate would be equal to the sum of the volume flow rate between in pipe 1 and pipe 2. Okay, these are the very important conclusive remarks in the case of pipes connected in parallel. Okay, so since HFA is equal to HFB is equal to HF, so we can tell that if it is like an equivalent head loss, so we can represent it as FELE by VE square by 2GDE is equal to FALA VA square by 2GDA is equal to FBLV VB square by 2GDB. Okay, and again if we want to eliminate velocity from all these expressions, we can represent velocity in terms of the volume flow rate, ratio of volume flow rate in the area of the pipe. So we get that if we then again simplify the expression, we will just go through the expression. Like if we simplify it, we get that root QA square can be written equal to K dA to the power 5 by C FALA. QB square is equal to K dB to the power 5 CFB LB. Then Q square will be equal to Q dE to the power 5 CFELE. Okay, where K is equal to some constant, like if all this value of all the head losses are equal, then let's say that this is equal to some constant, and C is taken to be this value. Okay, 8 by G pi square. So now we know that Q is equal to QA plus QB. Then we just take the value of the square roots and add it up. So square root of D to the 5 plus divided by FELE would be equal to square root of DA to the 5 by FALA plus square root of DB to the 5 FBLB. So if there are n number of pipes, we just extend this expression for n number of pipes. Okay, just extend this expression. Similar to that, the previous example, we can take this as a pipe in series connection. We can compare this parallel connection of pipes to a parallel connection of resistances in an electrical circuit. So since the potential difference between in an electrical circuit remains the same, similarly the head loss between the 2 points of this piping junction remains the same. Similarly, since the electrical current I is a sum of the current between the two in these two junctions, similarly the value of the mass volume flow rate in these two junctions piping network pipes will be equal to the sum of the volume flow rate between these two pipes. Okay, so we just take some examples. So let's take this example, simple example. Say there are two pipes of identical length and material which are connected in parallel. Diameter of the pipe 1 is 4 times the diameter of the second pipe. Assuming the friction factor and pipe length to be same in both the cases and disregarding minor losses, the ratio of the flow rates in two pipes Q1 by Q2 is question mark. Okay, so it is given that D1, so if it is the piping network, then it's told that D1 is equal to 4 times D2 and F1 will be equal to F2, L1 is equal to L2. Okay, so we know that HF1 is equal to HF2. So we have, again we simplify the expression in terms of volume flow rate and the diameter. So we get that 16 F1 L1 Q1 square by 2G pi square D1 to the power 5 is equal to 16 F2 L2 Q2 square divided by 2G pi square D to the power 5. Then we just cancel out the constants, 16 2G pi square, we eliminate the constants. Then again we have that F1 is equal to F2, L1 is equal to 2. So we have Q1 square by D1 to the power 5 is equal to Q2 square to the power D to the power 5. So we get that Q1 by Q2 would be equal to D1 by D2 to the power 5 by 2. Since we know that D1 by 2 is equal to 4, we substitute this value here, 4 to the power 5 by 2, which we get is equal to 32. So we have Q1 by Q2 is equal to 32. Okay, it's quite simple, it's pretty much simple and simple steps, but concepts need to be very clear. Okay, The concepts need to be very clear. Like we not need to be, we do not want to interchange the concept of series pipe and parallel pipes. Okay. Again, we take another example. Pipe A is connected in series with another pipe B, whose diameter is twice and length is 8 times that of pipe A. Okay. If both pipes have the same friction factor, the ratio of frictional head loss for pipe A to those for pipe B, that is HFA by HFB is. So we take this diagram. So it is told that diameter of pipe B is 2 times diameter of pipe A, and the length of pipe B is 8 times the diameter of pipe A. Length of pipe B is 8 times the length of pipe A. So and frictional factor, the value of friction factor in both pipe remains the same. Okay. So we need to determine the head loss, ratio of head loss at pipe A and pipe B. Okay. So we know that since we saw from the previous expression that the head loss and in an can be HF1 can be determined by this expression, this 16 F1 L1 Q1 square. Okay, let me just go by step, so it is simple to understand. So we know that HF is equal to HF1 plus HF2. Okay, so 16 FE LE Q square by 2G D to 5 pi square would be equal to 16 F1 L1 Q square plus 2G D1 to 5 pi square plus 16 F2 L2 square divided by 2G D2 pi square. Okay, this is quite simple. Okay, so basically this expression 16 F1 L1 Q square by 2G D1 to 5 pi square represents the head loss at for a particular pipe. Okay, for particular pipe. So now we need to determine the ratio of this head losses. So what we can simply do is take the ratio of this to this, right? So if we do that, again what we can do is we eliminate the constants from this expression. So what we can do, so we get that HFA by HFB would be equal to FALA by DA to the 5 divided by FBLB DB to the 5. So we got that FA is equal to FB, so this will cancel out. So we again got that we can write that LA by LB is equal to DB to the 5 by DA to the 5. Then we know that LA by LB is equal to 1 by 8 because LB is 8 times LA, and again DB is 2 times the diameter of pipe A, so it is 2 to the 5. So if we solve that, we get that HFA by HFB is equal to 4. Okay, so I guess I'll stop here today. There are some more problems. I'll share the notes so you can solve these problems as well. Like it's quite similar to what we have discussed in previous section. There's flow through pipes or head losses in pipes, so we can get in that. So thank you for today's session. I hope it was helpful. So if you have any doubt, please put your doubts in the discussion forum, and if you want to clarify the concept a bit more, you can always ask in the next session, or also join tomorrow's problem solving session, as well as if you have any doubts again regarding if you have any conceptual doubts regarding this topic, just again I would suggest that please go to the lectures once again, or of Professor Gupta, and again also you can follow his books for your concept clarification. Okay, so thank you from my side. So okay, thank you.